Salut tout le monde. Welcome back to episode 38 of my differential geometry reading series where I read Differential Geometry by Erwin Kreisig out loud on screen for you guys. I also interject lots of rants and add my own commentary. But today we're starting the last chapter of this book, which is chapter 8 on special surfaces. I would say the main, I've already skimmed it, so I would say the main parts of it would be the minimal surfaces part, and then the very end, the finale, where it sort of goes over surfaces of constant Gaussian curvature. So it kind of is tangential to the whole Riemann's inaugural Riemannian geometry paper, right? But it's not exactly that, and I've already mentioned this in other videos. This book is not without its criticisms as far as the thoroughness and how complete it is in treating the subject matter, especially from like a modern perspective. But hopefully I'll get through a few sections here, so I'm just gonna get right into it. Section 79, Definition and Simple Properties of Minimal Surfaces. A surface capital S of class R greater than or equal to 2, whose mean curvature, capital H, equal to 1/2 b sub alpha superscript alpha equals 1/2 b sub alpha beta then times g superscript alpha beta, where, of course, b sub alpha beta is referring to a component of the second fundamental form, and g superscript alpha beta is referring to components of the contravariant first fundamental form, because usually we present it with covariant subscript indices, so it would have been g sub alpha beta, but then you could just do a transformation on that so that you have the contravariant indices of the first fundamental form, which is g, and then the second fundamental form is b. And it says here, refer back to 41.10, which is actually really definition 41.2, which is just really the same exact statement as what's right there. But there's also another term, which is capital H equals 1/2 times quantity kappa sub 1 plus kappa sub 2 closed quantity, where those kappas are principal curvatures. So just more definitions of the mean curvature, but everywhere where this mean curvature is 0, that is at every point of the surface capital S, that is called a minimal surface. So it's like you're basically constraining the surface capital S to wherever it has this 0 mean curvature, and that is your minimal surface. So this name will be justified in the next section. We first state a remarkable property, an egregium property, perhaps, maybe that's a joke, of the spherical image of a minimal surface. Theorem 79.1. A surface of class R greater than or equal to 3 is a minimal surface or a sphere if and only if its spherical mapping, refer back to section 59, which is on the spherical image of a surface, the third fundamental form, and isometric mapping of developable surfaces, is conformal. The proof is as follows. We consider an arbitrary minimal surface capital S. Since capital H equals 0, we obtain from 59.7, which is just a statement of the coefficients of the third fundamental form, namely C sub alpha beta equals 2 times capital H times B sub alpha beta, then minus capital K times G sub alpha beta. We obtain from this C sub alpha beta equals negative capital K times G sub alpha beta, where, like I said, C sub alpha beta are the coefficients of the third fundamental form. This form plays the role of the first fundamental form of the spherical image of capital S. We see from the expression that I just read above that the coefficients C sub alpha beta and G sub alpha beta are proportional. Therefore, in consequence of theorem 61.1, which is an allowable mapping of a portion capital S of a surface onto a portion capital S star of a surface, is conformal if and only if When on S and S star the same coordinate systems have been introduced, the coefficients g sub alpha beta and g star sub alpha beta of the first fundamental forms of S and S star, respectively, are proportional. Namely, we have that g star sub alpha beta is equal to a function nu eta. That's what it is. These aren't news, they're etas, and I knew that. Anyways, eta in terms of coordinates u1 and u2, then times g sub alpha beta, where this function eta is positive, and we allow alpha to be 1 or 2 and beta to be 1 or 2. So in consequence of this, the spherical mapping of the surface capital S is conformal. That the spherical mapping of a sphere is also conformal is a trivial fact. We now consider any surface whose spherical mapping is conformal. Then, by the aforementioned theorem 61.1, we must have that c sub alpha beta is equal to this function eta in terms of coordinates u1 and u2, then times g sub alpha beta. Hence, the statement of 59.6, which is really the relation that ties together the first, second, and third fundamental forms. Namely, we have capital K, which is Gaussian curvature, then times I, which is the first fundamental form, then minus 2 times capital H being mean curvature, then times the second fundamental form, plus Roman numeral 3, which is the third fundamental form, all equals 0. So this then takes the form, okay, quantity capital K plus eta closed quantity, then times g sub alpha beta, then times du alpha, then times du beta equals 2 times capital H, then times b sub alpha beta, then times du alpha, du beta. We may assume that the second fundamental form does not vanish identically. Otherwise, the surface would be a plane and the spherical image would degenerate into a point. For Gaussian curvature equal to negative eta, we obtain that the mean curvature capital H is equal to 0. The surface is a minimal surface. Assuming that the mean curvature capital H is non-zero, we obtain another solution of the above relation. Namely, we have a fraction where we have capital K plus eta over a denominator of 2 times capital H. This is then equal to another fraction where a numerator is b sub alpha beta then times du alpha du beta all over a denominator of g sub alpha beta then times du alpha du beta, which thus is equal to kappa sub n. Hence, at every point of the surface, the normal curvature is the same for all directions. That is, the surface consists of umbilics only and is therefore a sphere, for which we can refer back to theorem 48.1, which states that if every point of a surface capital S, which has a representation of class R greater than or equal to 3, is an umbilic, the surface capital S is a plane or a sphere. There are no solutions of the previously stated relation 79.2 other than those indicated before. We stress the following very simple property. Theorem 79.2, minimal surfaces cannot have elliptical points. The proof is as follows. Since mean curvature is equal to 0, we obtain from 41.10, which, as I said before, that's just the definition for the mean curvature. We obtain from that the relation, I'm pretty sure that these are supposed to be kappas, which are on screen, because this is one of those OCR reads of the book. So to be consistent with everything else that's been in the book so far. Because I switched PDFs. If you're watching this for the first time, the earlier PDF that I was reading, someone basically just like cut out the really important pages basically out of the tail end of the book, which kind of indicates that, like, you know, these end sections, this really is where the important stuff is, because that person took the time to cut those pages out. But, you know, when I was reading that PDF, then you don't have those pages. Good thing I have the physical book, obviously, but then it's like you guys don't have that. Eventually, I found this new PDF, but those lowercase k's are really supposed to be kappas. So anyways, the relation kappa 1 equals negative kappa 2 and in consequence of 41.9, which is that Gaussian curvature capital K is equal to, whoops, there goes a little boy. Time for him to eat his lunch. Okay, anyways, good thing my coffee didn't spill. So, like I was saying, Gaussian curvature capital K is equal to the product of the principal curvatures. Principal curvatures are denoted as kappas. So kappa sub 1, kappa sub 2, kappa sub I, kappa sub n. Anyways, the relation 41.9 capital K equals kappa 1 times kappa 2, which is also equal to lowercase b over lowercase g, where lowercase b, of course, denotes the discriminant of the second fundamental form, lowercase g discriminant of the first fundamental form. Let's go. So in consequence of that, Gaussian curvature capital K, like I said, equals the product of the principal curvatures kappa 1, kappa 2, which then is less than or equal to 0. Since capital K equals b over g, like I said, discriminants of the second and first fundamental form respectively, and the discriminant of the first fundamental form, g, is greater than 0. At any point of a minimal surface also, b is less than or equal to 0. Thus concludes the proof, concludes section 79. We're on to now section 80, surfaces of smallest area. We will prove that if there is a portion capital S of a surface of minimum area among all portions of surfaces bounded by the same fixed closed space curve, then S must necessarily be a portion of a minimal surface. By that fact, the name minimal surface will be justified to a certain extent. Minimal surfaces are sometimes defined as surfaces with the property that any portion of them bounded by a closed curve capital C has the smallest area compared with any portion of a surface bounded by capital C. The curve, that is. But this definition by means of a minimum condition of the calculus of variation is not always satisfactory. We therefore prefer the definition by the property of identically vanishing mean curvature capital H. The situation is analogous to that in the case of geodesics. An arc of shortest length joining two fixed points on a surface must necessarily be an arc of a geodesic, but this condition is not always sufficient, for which refer back to section 51 on arcs of minimum length. With that, we come to theorem 80.1, which states, let capital C be a simple closed curve. If among all portions of surfaces of class R greater than or equal to 2 bounded by capital C, there exists a portion of, see, we lose a little bit here because in the book this x is bolded to denote a vector valued function. So we have x in terms of coordinates u1 and u2. There exists a portion of a vector valued function x in terms of coordinates u1 and u2 of minimum area, then so-called x in terms of u1 and u2 is necessarily a portion of a minimal surface. The proof is as follows. We compare the portion x in terms of u1 and u2 with portions vector x star in terms of u1, u2, and epsilon, which is equal to the vector valued function x in terms of coordinates u1 and u2, then plus epsilon times a function lambda in terms of coordinates u1 and u2, then times vector n in a neighborhood of the vector x in terms of u1 and u2. In this representation, the vector n is the unit normal vector to the vector x in terms of u1 and u2, and epsilon is a number of sufficiently small absolute value. In order that all these portions be bounded by the same simple closed curve capital C, we must require that the function lambda of u1 and u2 vanishes at all points of capital C. We have that x star sub alpha equals vector x sub alpha plus epsilon then times a quantity, lambda sub alpha then times vector n plus lambda then times the vector n sub alpha closed quantity, where lambda sub alpha is equal to partial lambda partial u alpha. Hence, by 27.1, which is just the definition for what the coefficients of the first fundamental form are, we have vector x sub alpha scalar product with vector x sub beta equals g sub alpha beta, where x sub alpha, for instance, represents a partial derivative of the vector parametric representation of curved surface, whatever you want, but it is along alpha, which is like a vector direction. So alpha is one, beta is another one. 38.4 likewise is definition for components of the second fundamental form b sub alpha beta equals negative vector x sub alpha scalar product with vector n sub beta. And actually right above 38.4 we have the definition for vector n sub beta. It's partial n partial u beta. So similar to how those vector x sub alpha or x sub beta are partial derivatives of vector x, n sub beta is a partial derivative of vector n, but along those different coordinate directions. So hence by those we have that g star sub alpha beta is equivalent to the scalar product of x star sub alpha with x star sub beta, which equals g sub alpha beta minus 2 epsilon lambda then times b sub alpha beta plus etc., where the dots, where I said etc., denote terms of order epsilon squared and higher order. From this we obtain that g star is equivalent to g star sub 1 1 then times g star sub 2 2 minus the square of g star sub 1 2, where these are components of the first fundamental form, but we have, stars here, so it's like, different, equals g minus 2 epsilon lambda then times quantity g sub 1 1 then times b sub 2 2 minus 2 times g sub 1 2 then times b sub 1 2 plus g sub 2 2 then times b sub 1 1 closed quantity plus etc. So like I said, we have on the right hand side one set of components of first and second fundamental forms, and then we get on the left hand side now different components of first fundamental form as indicated by the stars. Or because of 41.10, which I read earlier, that's again the definition of the mean curvature. We have that g star, discriminant of the first fundamental form, is equal to g then times quantity 1 minus 4 epsilon lambda capital H plus etc. closed quantity. Consequently, the square root of g star is equal to the square root of g then times quantity 1 minus 2 epsilon lambda capital H plus etc. So the square root is only over the discriminant of the first fundamental form outside that quantity of the 1 minus 2 epsilon lambda capital H plus etc. So according to 36.7, which is just a statement of the area capital A of H of a portion capital H of a surface capital S in terms of a vector parametric representation X in terms of coordinates u1 and u2, where we have capital A of capital H is equal to the double integral on the domain capital U of the integrand square root of g du1 du2, where this capital U is the domain in the u1 u2 plane corresponding to the portion of interest capital H. So according to this, the area capital A of epsilon of vector x star of u1, u2, and epsilon is given by the expression A of epsilon equals double integral of square root of g star du1, du2 on B is equal to the double integral on B of the square root of g du1, du2, then minus 2 epsilon times the double integral on capital B again of the integrand lambda times capital H times the square root of g du1, du2 plus etc., where capital B here denotes the domain in the u1, u2 plane corresponding to the range of values of the vector function x in terms of u1 and u2 in the interior of C. So we took that expression for the area of a portion H of a surface, and our domain is B. It's that range of values of the vector function x in the interior of C. That's what the u would have been. And then we just plugged in again the square root of the discriminant of the first fundamental form. If x of u1 and u2 is equivalent to x star of u1 and u2 and 0, so epsilon is 0, among all portions x star of u1, u2, and epsilon of surfaces is to be of minimum area, we must necessarily have d capital A of epsilon d epsilon evaluated at epsilon equals 0 is 0. Consequently, the second integral on the right-hand side of what I just read in 80.1 must vanish for any portion x star of u1, u2, and epsilon, that is, for any choice of the function lambda in terms of u1 and u2. We therefore must have that the mean curvature capital H is equal to 0. This completes the proof. In 1866, Plateau, that is Joseph Plateau, who lived from 1801 to 1883, illustrated by his experiments that portions of minimal surfaces can be realized as a soap film by dipping a wire in the form of a closed curve into a soap solution. The problem of finding a minimal surface is therefore also known as the problem of plateau, and we can refer to one of the works in the bibliography that are by Tibor Rado. And Tibor Rado lived from 1895 to 1965. He was Hungarian, and actually one of the works referenced in the bibliography, he collaborated directly with Erwin Kreyszig on. So, Theorem 80.2. If a portion S of a minimal surface of class R greater than or equal to 3 is bounded by a simple closed curve C of length L, and if the area A of S of the portion S is a minimum, then A of S is less than or equal to L squared over 4 pi. The proof due to Blaschke is as follows. We consider a cone with apex at an arbitrary fixed point on C whose generators pass through C. Let S star be the portion of that cone bounded by C. S star is developable and can therefore be mapped isometrically into a plane, for which refer to Theorem 59.3, which states that a sufficiently small portion of a surface of class R greater than or equal to 3 can be mapped isometrically into a plane if and only if it is a portion of a developable surface. And as a reminder, a ruled surface first is generated by a one-parameter family of straight lines, namely vector x in terms of s and t, where s is arc length and t is a floating parameter, scalar. This is equal to vector y in terms of s plus parameter t, then times vector z in terms of s. Then, additionally, furthermore, a developable surface is a special ruled surface where the tangent plane at all points of any of its generators is the same. So different types of a developable surface include planes, cylinders, cones, and tangent surfaces. And the relation that I just said, where we have y of s plus t times z of s, is a developable surface if and only if the determinant, where column-wise we have vector y dot, and then we have the vector z, and then we have the vector z dot, this is equal to 0. And a surface is developable if and only if its Gaussian curvature is 0. Isometric mappings are equiareal, and we can refer back to Theorem 66.2 at this point, which states 1. Every isometric mapping is equiareal, and 2. Every equiareal and conformal mapping is isometric. As is well known, among all portions of a plane bounded by a simple closed curve of length L, the circular disk has the maximum area given by A equals pi r squared, which equals L squared over 4 pi. Since S is assumed to have the minimum area, A of S, we must have that A of S is less than or equal to A of S star, which is less than or equal to A. From this, the above inequality follows. We finally mentioned some facts of the history of minimal surfaces. The problem of determining portions of surfaces of minimum area with given boundary was first investigated by Lagrange. Moisnier discovered the fact that for a portion of a surface which solves that problem, we must always have that the mean curvature H equals 0. And remember, Moisnier is from Moisnier's theorem, which is Theorem 39.2, which I'll give you a different way of stating it from how it's stated in the book, which is from Wikipedia. All curves on a surface passing through a given point P and having the same tangent line at P also have the same normal curvature at P, and their osculating circles form a sphere. I think that's a better way of putting it than what's in the book, but that's Jean-Baptiste Moisnier. And actually, he announced that in 1776. So that's the same year that not only was America founded, but that was also the year of the publication of Wealth of Nations. And it's also the year that Jane Austen was born, the author of works such as Pride and Prejudice, Sense and Sensibility, and Mansfield Park. But so Moisnier's theorem came out in 1776, but it wasn't published until 1785. And actually, Moisnier was a French revolutionary general, or a general in the French Revolution, and he formulated his Moisnier's theorem while he was at the École Royale du Génie, which is the Royal School of Engineering. Fun facts. Moisnier discovered also the first special minimal surfaces, namely the catenoid and the helicoid, which we're going to go into further in this chapter. Further progress was obtained by Alfred Enneper, who lived from 1830 to 1885. Interestingly enough, Enneper earned his PhD from Göttingen University in 1856 under none other than Dirichlet, and Enneper was a contemporary of Karl Weierstrass. We're going to see Weierstrass later in this chapter as well here. What did I just say? The results of Weierstrass are important especially because of the fact that, on the one hand, they permit the investigations of problems on minimal surfaces in a general manner, and on the other hand, they make it possible to discover new types of minimal surfaces. We will study the so-called formulae of Weierstrass in section 82. Further progress in the theory of minimal surfaces was made by Riemann, Schwarz, that is Karl Hermann Amandus Schwarz, that's who H.A. Schwarz refers to from the bibliography, Sophus Lee, a big name that we're going to get into, and Albert Ribelcourt. Ribelcourt lived from 1845 to 1893. He was French-Algerian, an engineer and mathematician, and of course, Tibor Radot. We also have here a reference to Jesse Douglas. Jesse Douglas lived from 1897 to 1965. And actually, Jesse Douglas, J. Douglas, okay, it says here, obtained the following general solution of the problem of plateau. Given a simple closed Jordan curve, capital C, there exists at least one portion of a minimal surface bounded by capital C. So, interestingly enough, this guy, Jesse Douglas, an American, was one of two of the first Fields medalists. So the first Fields medals were awarded in 1936, and Douglas was one of those recipients for his 1930 solution of the problem of plateau. And interestingly enough, the other first Fields medalist was Lars Alfors, so the author of the famous complex analysis, the tome. It's not a tome, it's not that big, but that's like the reference on complex analysis, if I do say so myself. And another fun fact here, well, a couple, I guess. Jordan curves and the Jordan curve theorem are named after the French Camille Jordan, who lived from 1838 to 1922. And the problem of plateau is also referred to as the soap bubble problem and is part of the calculus of variations. This has been a lot so far. I was maybe going to read section 81 as well, but that's a little more involved. There's also two problems at the end of section 81, which we haven't read any problems in a while. So that section, while it may be, only a few more pages from what I just read, there are also those problems. So I think I'm going to cut it off there. Yeah, there's a lot more to talk about, but I'll see you guys in the next one. Peace.